Again, this is Professor Ramsey, and this is the third and final of our introductory videos discussing basic statistical concepts we'll use throughout the semester in design of experiments. So in the previous section, we discussed what are called confidence intervals. Remember, these are statistical techniques we use to try to draw inferences or conclusions about the values of theoretical parameters of a distribution, and our primary focus was on a confidence interval for the theoretical mean of a distribution. And we usually use the Greek letter mu to represent that theoretical constant. So remember, for a normal distribution, which will be our primary distribution we'll use this semester, that's a theoretical distribution. It's the bell-shaped curve, and there is an equation that describes that curve, and that curve requires that we have values for the theoretical constant mu, the mean, and the theoretical constant sigma, the standard deviation. And as I mentioned previously, we just use the sample mean and the sample standard deviation to estimate them. But as we've said repeatedly, those sample estimates are in no way the theoretical values. They're just estimates of those values. So we use the method of confidence intervals to compute a range of values within which the theoretical value might lie. So we ended up saying things like we're 95% confident that the theoretical mean is between some value, let's just call it value A to value B, and we're quite confident the theoretical value is in that range. So we would call that a form of statistical inference. Well, as I mentioned last time, there is another form of statistical inference called hypothesis testing. And it turns out hypothesis testing is actually older than confidence intervals by quite a bit. And confidence intervals actually came about in about the mid-30s. Hypothesis testing is probably well over 100 years old, but was formalized by R.A. Fisher, the man who literally invented design of experiments. Well, unlike statistical intervals where we collect some data, use a statistical formula, and compute a range of plausible values for the theoretical parameter mu, or whatever parameter you're interested in, like sigma, the standard deviation. In hypothesis testing, we begin by constructing hypotheses about what the actual values might be of these theoretical parameters, or basically unknown constants. Then we collect some data, and then we test the hypotheses. Basically, we compare the hypothesized value to the sample data, and we see if they're in agreement. If they're not, we reject the hypotheses. If they are, then we simply say that the data are likely under the assumption of the null hypothesis. Okay. And the easiest way to explain hypothesis testing is to simply show examples. Again, our focus will be on hypothesis testing for the theoretical mean mu, again a parameter of a distribution, and again we'll assume we're interested in mu, the theoretical mean of a normal distribution. Okay. So we're going to construct a hypothesis as to what we think the theoretical value or values might be. We'll collect some data, and we'll use a statistical test to determine the level of agreement between what I hypothesized and what I actually observed. If they're in good agreement, then I will not reject the hypotheses. if there is considerable discrepancy, we'll explain how we define discrepancy in a moment, I reject the null hypothesis and say it is false. Okay. So in hypothesis testing, as originally developed by R.A. Fisher, we begin with what he called a null hypothesis, symbolized commonly by a capital H with a subscript 0. And the null hypothesis is your statement of belief about what the true value of the population parameter might be. Again, we're going to focus on the theoretical mean mu, which has the most meaning for design of experiments. So we state a hypothesis. If the data is not in agreement with the null hypothesis, then we reject it. Rejection leads to what we call accepting an alternative hypothesis. So I state a null. If I reject the null, I automatically accept another hypothesis called the alternative. When you see an example, you'll see the alternative is actually quite obvious and for the most part doesn't even need to really be stated. Okay. So we're going to state a null, collect data, use a statistical procedure, and to measure the level of agreement between the null hypothesis and the data. If the discrepancy between the two is sufficiently large, we simply will reject and accept an alternative. Okay. So when we do hypothesis testing, it's basically an algorithm. It follows the following simple steps, which we'll illustrate momentarily, within a moment actually. You state the null hypothesis and you assume it's true. Okay, so we're going to state some hypothesized value for the theoretical mean, and then for purposes of doing the test, we'll assume it's true. Then we collect the data. Then we use what we call a test statistic. This is a measure of agreement, as you'll see in a moment, between the null hypothesis and the data. And then based upon the value of that test statistic, we decide whether or not to reject the null hypothesis. Okay. If the level of agreement is low between the null hypothesis and the data, we reject, and if we reject, we accept an alternative. You'll see this actually follows a quite logical pattern, and basically once you get the hang of it, it's actually quite easy to do these tests and to interpret them. Okay. So slide 6 basically gives you the algorithm or the structure or the flow of how the test is done. Okay. So we're going to focus in this section on something called a one-sample t-test. This is one of the most basic types of hypothesis tests, yet in design of experiments we'll see it's actually quite useful. And it's called a t-test because the test statistic that is used as part of the test is based upon the student t-distribution, the very same one that we discussed during confidence intervals. So I'm going to assume we've previously discussed students t to construct confidence intervals. Now we're going to see it's commonly used in hypothesis testing. Okay. So again, first we're going to state a null hypothesis for the theoretical mean. Again, our focus for the most part in design of experiments will be on the theoretical mean. And if we reject that hypothesis, meaning the hypothesis and the data are not in good agreement, we'll accept an alternative. Okay. So to illustrate the procedure, I'm going to use a simple example. This is a data set which contains the measure of output in lumens of 7 fluorescent lamps. Okay, so I have 7 lamps. We measure their outputs in lumens, and the target for these lamps is 3,500 lumens. So they've been engineered to, on average, produce 3,500 lumens. So we pick a random sample of 7 lamps, and then a technician measures the intensities, and you can see on slide 8 there are 7 measurements. Furthermore, here are our sample statistics. Okay. The average was 3,414.3, and the standard deviation was 481.1 lumens. So the average is not 3,500. I don't expect it to be, because X bar, the average, is a statistic, and every time we were to take a new sample, we'd get a different average. The question is 3,414 close enough to 3,500 that 3,500 may indeed be the true mean? In other words, are they close enough or in agreement, in sufficient agreement, that it lends support to the null hypothesis? Okay. So I have the average, and then again notice the standard deviation is relatively large. In other words, the average variation lamp to lamp is almost 500 lumens, which is quite large, but that's the reality based upon the data. Okay. So when we perform these hypothesis tests, again, we state a null and an alternative. So notice on slide 9, the first way I state the hypothesis is something referred to as a two-tailed or two-sided test. Notice the null hypothesis is quite simple. The mean, the theoretical mean, equals 3,500 lumens. Notice if I reject that, I simply say the mean is not 3,500. It's a very general test. The alternative is really obvious. It's called two-sided because under the alternative, the mean could be less than or it could be greater than 3,500. We simply leave it wide open and say it could be less or it could be greater. You can also state these in terms of one-sided hypotheses. Occasionally we'll use these. For the most part, we'll use two-sided. So notice under one of the one-tailed tests, or one-sided, the null is the mean is greater than or equal to 3,500. If I reject that, the mean is less than 3,500. And then there's another way I could state it, which is actually quite logical. Under the null, the mean is less than or equal to 3,500. And then under the alternative, again, it's greater than 3,500. So when we talk about one-sided and two-sided, you can typically look at the alternatives, and that will determine whether it's two-tailed or which one of the one-sided tests are done. The good news in statistical software packages, they literally do all 3 of these tests, and they leave it up to the analyst to decide which one he or she would prefer to use. Okay. So basically, we're going to reject the null hypothesis if the sample average is either much larger or much smaller than 3,500. So if there's a big discrepancy between the sample average and my hypothesized value of 3,500, that would lead to rejection. The question is, how do we judge the relative amount of difference in terms of significance between the null hypothesis and the sample average? Well, that's where the student t-distribution is going to come into play, as you'll see later in the slides. Okay. Well, one of the interesting aspects of hypothesis testing is that any hypothesis test, and believe me, there are thousands of them, most of them would be well beyond our scope, and we're going to stick with some of the most commonly used hypothesis tests. But these hypothesis tests produce a summary measure of the agreement between the null hypothesis and the test statistic. And this measure was invented by R.A. Fisher in the 1920s, and he called it a p-value, where p stands for probability value. Okay. The p-value is a measure of the agreement between the null hypothesis and the data. A small p-value, and often, and this is arbitrary, a value of 0.05 is used, indicates that if the null hypothesis were true, then the observed data would be improbable or unlikely. So a small p-value, meaning assuming the null hypothesis is true, then the observed data is unlikely, then we reject the null hypothesis. In other words, the data indicates the null hypothesis should be rejected. It is not valued or valid. So you'll see that these p-values form a basis for our decision as to whether or not to reject the null hypothesis. You'll also notice in JUMP that they denote p-values in the form of the test statistic that's used. And again, there are thousands of different types of hypothesis tests, some of them very esoteric and hard to understand or explain the mathematics. The good news is all hypothesis tests generate p-values. Small p-values indicate the null hypothesis is highly unlikely because the level of agreement between the data and the hypothesis is small. In other words, if the null hypothesis were really true, the observed data is not probable. Hence, the null hypothesis must be false. Okay. So in slide 11, we simply point out the p-value. It is a probability value, meaning it has to take on a value between 0 and 1 because all probabilities are defined on a scale of 0 to 1. 0 meaning something could never occur, 1 meaning something would always occur. So when we look at p-values, the higher the p-value, the less evidence there is against the null hypothesis. The small p-value indicates strong evidence against the null hypothesis. And this may be a subtlety, but you can never prove a null hypothesis is true. It's impossible because that would require me to know exactly what the true theoretical value of the parameter is. For the sample the example we're just using with the fluorescent lamps, I would have to know exactly what the true theoretical mean of that process is. Since I don't, and I never will, I can never say with complete certainty the null hypothesis is false, nor can I say it's true. But what I can do is look at the data and say the data provides evidence for or against the null. And again, if the p-value is small enough, we typically by convention just reject the null. But failing to reject the null is not proving it's true. It just says, just as they say in law, there is insufficient evidence to overrule the null hypothesis. And that's where we leave it. Okay. Now, these p-values or probability values are, to use a word, ubiquitous in statistics. They're everywhere. And through the course of the semester, I'm going to point out that these p-values, although they provide a summary measure of evidence against the null hypothesis, and every hypothesis test generates a p-value, they're not without their difficulties. One of the nice things about them, they're easy to interpret, relatively easy to calculate in most cases. But on the other hand, just like the term confidence for confidence intervals, people sometimes overinterpret them. Okay, so remember the key point. We assume the null hypothesis is true. Then we measure the agreement of the data to the null hypothesis. This agreement is measured by a p-value. If the p-value is small, that indicates the null hypothesis is improbable. So a small p-value would indicate that our test statistic assumed an extremely large or small value way out in the tails of the possible distribution. So again, I assume the null hypothesis is true. Okay? So when I assume that, what that does, it allows me to assume that my test statistic follows a known probability distribution, for the present case a student t distribution, and I simply see where that test statistic falls in the tails of that distribution. If it's way out in the tails, that indicates that there's poor agreement. We reject the null. Now, 0.05 is typically selected as the cutoff, meaning there's only a 5% chance I could have gotten a more extreme value of the null hypothesis. In other words, if I were to look at a student t curve, my test statistic fell well out in the tails. Now, the problem of that 0.05 is it's completely arbitrary, and its exact origins in the history of statistics are unknown. However, today it is commonly taught if the p-value is under 0.05, reject. If it's above that, don't reject. And I will challenge that as we go along because there is no logical basis for it. But it is so commonly taught and ingrained in people's minds, they tend to think there's something very special or magical about 0.05. There is not. And as I said, we don't even know where 0.05 came from. It just suddenly started appearing in the literature in the 1930s, and now it is just a common statistical practice. And why 0.05? Well, 0.05 says there's only a 1 in 20 chance that I'll incorrectly reject the null hypothesis, meaning only 5% of the time using this method would I reject a null hypothesis that turned out to be true. Okay? So that turns out to be very useful to us. Okay? In some sense, that makes sense. Well, I only want to have a small chance of incorrectly rejecting the null hypothesis. The problem is, who says it should be 1 in 20? Could it be 1 in 10? Could it be 1 in 50? The answer is, it's really up to the person doing the analysis what risk he or she wants to take of incorrectly rejecting a null hypothesis. So there are nothing but actually rough guidelines for these p-values. Again, this idea of hypothesis testing and p-values were invented by R.A. Fisher as a way for scientists to evaluate the results of their experiments and then judge what results might be significant and what might not. And to Fisher, significance simply meant of interest. Well, he showed them how to calculate the p-values, but that led to an important question. Well, that's fine. We've learned how to calculate p-values, but what rules do we use to reject the null? Again, Fisher actually never gave hard and fast rules. In fact, he argued against it. But on slide 13 at the bottom, you see some of the common rules. Under 0.05, reject. 0.05 to 0.15, consider the risk of incorrectly rejecting the null and perhaps even getting more data. Above 0.15, don't reject the null, but I caution everybody over and over again that the problem with this is these are arbitrary. So we're going to teach hypothesis testing and p-values. You'll get some experience with them. I have to keep reminding you that this 0.05 rule is quite arbitrary, and there are many statisticians today who don't even subscribe to it. In the end, it's really up to you, the analyst. What's the risk you're willing to take of incorrectly rejecting a null? That is, the null hypothesis is true, but you reject it. That risk determines the p-value. Okay, so how do we do the one sample t-test in JUMP? Well, it's done in the distribution platform, and I'm going to show this in a moment. And in the report menu, it's something called test mean. Okay, so what I'm going to do is go over to JUMP and open up the data set. And which one do I want to use? I'm going to open up the data set lumens. This is the data I just introduced as part of the example. Okay. So there are our 7 lamps and our 7 measurements. So go to Analyze, Distribution, because once again I'm trying to draw some conclusions about the distribution of lumens. Okay. So I put lumens in Y since it's my only measured response. Okay. And we get our summary statistics report. You'll see the statistics match what we showed in the original example. And then in the report menu to the left of lumens, okay, there's something called test mean. All you need to fill out in this dialog box is what's the theoretical mean value that you've hypothesized. So in the study we said 3,500. And in a little bit, I'm going to actually fill in a little bit of the mathematical detail behind the test. I'd like to introduce the test first. So notice I've hypothesized 3,500, and the actual sample average is 3,414.29. Okay. So we calculate something called a test statistic. Again, I'm going to show that in a moment. Okay. And the test statistic value is minus 0.47. What that 0.47 is, that's the number of standard errors between the sample average and the hypothesized mean. Remember, the standard error is the standard deviation of an average. The t-test is focused on averages, not on the raw data. Okay. So the question is, okay, if the null hypothesis is true, how likely am I to see a test statistic value of 0.47? Well, the way we do this, and JUMP gives us some nice visual displays, is we assume that the distribution of sample averages follows students t. I explained that in the confidence interval section. So under the null hypothesis, I assume that the distribution of averages follows a student t distribution, and guess what? It's centered at 3,500. Okay. So this curve that you're looking at, what that describes is the range of possible sample averages that I could see in practice if the curve were really centered at 3,500. Again, this curve you're looking at is a student t curve, and it's an assumption I'm making about the distribution of sample averages. I mean, I have to make some sort of a draw some sort of assumption as to what that distribution looks like in order to evaluate the hypothesis. So what we've discovered, that the actual sample average is 3,414.3, okay, And notice there's a vertical line drawn on the curve at that value, 3,414. Well, this is a two-sided test. That is, under the alternative hypothesis, I will simply say the actual mean could be less than 3,500 or greater. So in a two-sided test, I actually have to evaluate the hypothesis on both sides of the null. So what we do on the other side is draw a line at the same distance from 3,500, and then that line defines a region on the other side of the sample mean, okay, and allows us to evaluate the probability the mean could be greater than 3,500 or less than 3,500. The area, the shaded area under the curve, represents the probability that I could have gotten a sample average, okay, more extreme than the one I observed. In other words, what proportion of the distribution of possible sample averages is less than or greater than the value I observed? And the answer is given to us, 0.654. In other words, about 65% of all of the possible values that I could have observed if the null hypothesis were true, okay, are either less than 3,414.3 or equivalently about 3,586 on the other side. In other words, I go an equivalent distance the other way. This is what a p-value measures. What's the probability I could have gotten a more extreme value? Well, the answer here is it's pretty high. That's another way of saying the sample data are really in good agreement with the null hypothesis. Why? Because 3,414 is actually pretty close to 3,500. Well, how do we measure closeness? We calculate the p-value. That was Fisher's solution. So the p-value is just the probability. Look at the shaded areas under the student t-curve. It's just the probability I could have seen a more extreme value. So in this case, we do not reject the null hypothesis. In other words, the discrepancy between the sample average and the null hypothesis is so small we have no evidence to reject the null. It's entirely possible that the theoretical mean is 3,500. I can't really prove it, but I have no evidence against it. And by the way, take a look at my 95% confidence interval for the theoretical mean. 3,500 is almost right in the middle of that range. So both the p-value in the hypothesis test and the confidence interval lead to the same conclusion. Based on the sample data, 3,500 is a plausible value for the theoretical mean. I'll never prove it, but the hypothesis test and the confidence interval provide evidence that 3,500 is plausible. It could be. Okay. Now in JUMP, they have a nice, excuse me, that cough again. They have a nice little tool in the test mean procedure. So click on the menu to the left of test mean, the down arrow, and select p-value animation. Okay. So it's a nice little tool to try to help explain the concept of the p-value. Okay. So let me spread this out a little bit for you. Okay. I'll pull it in a little bit. Okay. Again, this is exactly the same scenario we were just looking at. Theoretical mean is 3,500, so we center our student t-curve at 3,500. Okay. The vertical line to the left is 3,414.3. And because this is a two-sided test, under the alternative, I said the mean could be less than 3,500 or greater than 3,500, we actually look at both sides of the distribution below 3,500 and above. So even though our original line is at 3,414, the observed sample average, equivalently we go the same distance to the other side of 3,500 and draw in a line, and that gives us two areas under the tails of this distribution. So for a two-sided test, this becomes the p-value. And as I've said, that p-value, if I can capture it here, you can see it, is about 0.654, meaning that 65% of the possible sample averages are more extreme than the ones I observed. So this is how we define the p-value. Okay. Technically, it measures the probability of getting a more extreme value if the null hypothesis is true. Well, let's change the hypothesis. Well, notice the little handle above the curve. I can drop and I can drag it and come up with a new hypothesis. Well, suppose that my hypothesized mean, let's pick a value here somewhere. Okay, so let's say the hypothesized mean, I'll round it off, was 3,865. Okay, so that's my new hypothesis, and of course the sample average is what it is. The data have been collected. So in this scenario, and I'll show the t-ratio calculation in a moment, but notice the p-value. Okay. 0.0, well, let's round it off, 0.05. Okay, so we're really in a borderline situation in terms of rejecting the null hypothesis. Our p-value is close to 0.05, but notice that this indicates there's now a bigger discrepancy between the sample average and the hypothesized value. They're farther apart. Furthermore, if the hypothesized mean were really 3,865, the probability I might have observed a more extreme value of the sample average is pretty small. So in this case, it's borderline. So in this point, you probably, if you rejected the null hypothesis, you'd do so without a lot of confidence. You might actually consider wanting to collect more data. Let's keep going. Let's go to an even more extreme hypothesis. So I'm going to go out to close as I can get it. 4,000. Let's round it off. The null hypothesis is 4,000. I assume it's true. So now the question is, what's the probability of observing a more extreme value of the test statistic, 3,414, the sample average, given the theoretical mean is 4,000? The answer this time is pretty small. The p-value says literally about 0.02, okay, or only, get this to go right, about 2% of possible values of the sample average would be more extreme than the one I observed. Again, this is a two-tailed test, so we calculate area under the tail, equivalent areas on the left-hand side and the right-hand side, because under the alternative, I have not specified the mean to be less than 3,500 or greater. Well, using statistical convention, the p-value is less than 0.05. I reject. Well, what if, by the way, it doesn't matter which side of the direction I move in changing the hypothesis. In other words, I could equivalently do the study moving to smaller means, but just because of the way the display is drawn, it's easier for me to just go to larger values. Let's move even further out. click and drag the handle if I can get it there. There we go. Let's go out to oh, 4,200. Well, notice now we can barely see any area under the tails of the distribution. And in point of fact, if the theoretical mean were truly 4,200, then about 0.5% of possible sample averages would be more extreme than the one we observed. As a result, in this particular case, we would not reject the null, we would overwhelmingly reject the null hypothesis. In other words, the discrepancy between the theoretical hypothesized mean of 4,200 and the observed value of 3,414 is so extreme that there is little evidence that the null hypothesis is true, and we would simply reject it. Okay. Now let's take a look at a one-sided test. So this is a two-sided test. And I'm going to regenerate this, or I'll have you all confused. So I'm going to just regenerate the animation. Okay. Let me expand it out for you. Okay. And this time, instead of the two-sided test, let's do a one-sided test. Okay. So what is this test? This is a test that the actual mean is less than 3,500. This is a one-tailed test. So notice for the one-tailed test, we only look at the tail area of the t-distribution below 3,500. So I observe 3,414. Okay. So that says the probability I could have gotten an even smaller value is 0.327. In other words, of all the possible theoretical, or based on the theoretical mean being 3,500, about 33% of all sample averages that I could observe would be less than 3,414. I do not reject the null hypothesis. It's a fairly large p-value. Well, what about the high side? Okay. This is the probability that the mean is greater than 3,500. Okay. Well, it turns out that under the hypothesis is that the mean is 3,500, about 67% of all sample averages could have been greater than 3,414. So once again, I would not reject. So basically, all three forms of the hypothesis test lead to the same conclusion. It's entirely possible that the theoretical mean of this distribution is 3,500. Okay. So if you look in the test statistic report, you're given all three forms of the test. The probability the mean is greater than 3,500, the probability the mean is less than 3,500, and the first one, the one we'll mostly focus on, the mean is not 3,500. Again, the p-value measures the level of agreement between the null hypothesis and the sample data. So in my case, the p-value is 0.654, which says 65% of all possible sample averages I could have observed are either less than 3,414 or greater than and I draw an imaginary line the same distance on the other side, so close to 3,586, or greater than. Hence, the value I observed is highly probable. So I do not reject the null hypothesis. So if you look through the notes, we go through an explanation. We do a couple of more examples. Here's an example using the aluminum lithium data, and I once again use a two-sided test. The theoretical mean is 175 KSI. Okay, I reject that. The alternative, it's not. Okay. So we do the test. Notice I hypothesized 175. The sample average is 162.7. Okay, it turns out that's actually a big discrepancy. And if I take a look at my student t distribution, the theoretical one centered at 175, notice the discrepancy between 162.7 and 175 is so large you can't even see the tail area. In other words, only about 0.16% of sample averages could be more extreme. Therefore, we reject. This p-value is so small, we'd say there's no way we would have observed 162.7 if the theoretical mean were actually 175. Okay. And I showed you the p-value animation, so I'm not going to repeat it. In fact, I'm going to move beyond some of this, and I explained the one-tailed tests, so I'm not going to spend more time on it. And the last part of this describes the arithmetic behind the student t-test. Where does it come from? Well, first of all, the student t distribution, I said it's a cousin of the normal, and to the left is what we call the student t statistic. Notice it's the sample average minus the theoretical mean divided by the standard error. So if my theoretical mean is 3,500, okay, then that would be x bar minus 3,500. X bar is the sample average. 3,500 is what I've hypothesized. And at the bottom of the slide is the calculation. Notice what this is. Notice the numerator. Let me just draw in the numerator. This is the distance between the sample average and the hypothesized value. Okay. The greater the distance between them, the least likely the null hypothesis is true. But once again, remember the sample average, 3,414.3, is a statistic. So I can't just look at the arithmetic difference and make a decision, because x bar is a random variable. I know that every time I got a new sample, I'd get a new average, and that distance would change. So how do we come up with some yardstick to judge whether or not that distance is significant? Well, look at the denominator, the standard error of the mean, or the standard deviation of the mean. What it is, it's a measure of the noise in the sample average. So what a t-ratio is, and what Fisher intended it to be, is a signal-to-noise ratio. The numerator is a signal indicating that whether or not there's a difference between the sample average and the theoretical mean that's been hypothesized, and the denominator is a measure of the noise in my sample average. Well, notice that the difference between 3,414.3 and 3,500 is basically less than one standard error, or one standard deviation. So if, by the way, positive or negative is not really of interest here directly, it's the magnitude. So basically the difference between the sample average and the hypothesized 3,500 is a signal-to-noise ratio of about 0.5. Now I know in theory and engineering the minimum signal-to-noise ratio is 1, but in statistics, because of the sample variation, we can get them less than 1. Okay. By the way, in theory, it would be basically 1 would be a guideline for a signal-to-noise ratio. But we're going to show that you can look at it more formally. So that t statistic is pretty small. So gee, they're pretty close to each other. They're less than a half a standard error. By the way, in statistics, that means they're almost the same value. They're so close together. But how do we judge that distance? What's a great distance? In other words, a big distance. Well, if I use the student t distribution and I went to a student t table, and just as I did for confidence intervals, I looked up a percentile. Well, my percentile is once again going to be the 97.5th. In other words, my p-value basis for rejection is 0.05. That 0.05 is the risk of a false rejection, meaning I rejected the null and it turns out it was true. But I'm doing a two-sided test, so I take that total risk of 0.05 and I split it in half between the lower end of the distribution and the upper end of the student t distribution. So basically 2.447. Or if you wanted to look at both sides of the distribution, minus 2.447 or 2.447. Well, it turns out that if my sample average led to a t statistic that fell exactly on one of these two values, the p-value would be 0.05. If it's outside of these two values, the p-value is under 0.05 and we would reject. So basically what's going on with this student t distribution, if my t-value falls outside of these percentiles, and again we mostly just use the magnitude or absolute value and just look at the upper end for convenience, we would simply say if I got a t-value greater than an absolute t-value greater than 2.447, we would reject. However, we don't really need to go to t-tables and look up percentiles, because statistical software generates these p-values. So the p-value, what it's actually measuring is what percentage of the tail area of that student t curve would be more extreme than what we actually observed. So if it's under 0.05, we reject. Meaning there's only a small probability we'd have observed a value that extreme under the null hypothesis. Okay. So basically what that tells you is there's a 5% risk that I could reject the null hypothesis in error. Okay, so 0.05, again, I point out it is arbitrary. We don't even know where 0.05 became the basis for rejection. It's commonly taught. I do not in any way rigidly enforce it. In fact, the key is what really is your risk of incorrectly rejecting the null hypothesis. In a discussion later on in Chapter 3, I'll talk more about that risk and an assessment of it. But 0.05 is a guideline, and I would leave it at that. Don't overinterpret it. Okay. So I'm going to skip it. So basically, this has been a straightforward introduction to hypothesis testing. Again, there are many, many types of hypothesis testing. You will see many of them going forward. The takeaway from this section would be to at least get comfortable with the concept of a p-value and how to interpret it, because that is what you'll see as we going forward in a lot of the jump statistical output or any other software package. Okay, so this concludes the third and final introductory video on statistics. So I've described descriptive statistics, I've described confidence intervals, and I've given you the fundamentals of hypothesis testing. Again, on hypothesis testing, the idea is I fundamentally state or conjecture a value for the theoretical mean of the distribution. And by the way, as I said, hypothesis tests are for many other parameters. Our focus is on the mean. Okay. Then I get some sample data, and I assume the null is true, and I assume the sample averages follow a student t distribution. In other words, I assume that's their theoretical distribution centered at the null hypothesis, and then I just see how far out in the tails of that theoretical student t curve my actual observed value fell. And if it's far enough out in the tails, and that is beyond the 5% region, I reject. Okay. So p-values lead to a nice, simple, in fact, in some ways, too simple way of trying to evaluate a null hypothesis. So from here on out, you're going to see the hypothesis testing, and you'll see other variants of it, a few others as we go along. What I'd like you to do at this point is at least become comfortable with what a hypothesis test is, the null, the alternative, and how to interpret a p-value.